Good. So today we're going to talk about transfer and also begin our discussion of multitask learning. But before we get into that, a few class notes. So the project milestone is due next week, so hopefully all of you have made progress on your final project. We'll post more detailed instructions on Piazza very soon, but the high-level bit here is that we'll have the same sort of peer review process. So all of you will submit your project milestone reports, and then within a few days, maybe 5 days or so, you'll also get feedback from your peers, and that's mainly for your benefit to get a sense for how you're progressing, and maybe your peers will also make some suggestions about how you could improve your project. And of course, the TAs will also look at the project milestone reports and also give you feedback on that. So do make sure that you make some progress before the milestone report. It's really meant to be primarily for your own benefit so that you can get some advanced idea of how your project is coming along before the final report at the end of the course when your grade will be based on that. So this is your opportunity to get a sense for how things are coming along. So do make sure you take advantage of that. Get some progress on your final project before the milestone report, and write up everything that happened. Homework 4 is due tonight, so hopefully you're all in good shape with that. And then homework 5 will be released shortly. What we'll probably do for homework 5 is we'll actually release most of it today, and then we have one small part that we'll also release on Friday after the meta-learning lecture. So the scheme for homework 5 is actually going to be a little different. Homework 5 is meant to give you some practice implementing some of the more advanced methods that we discussed in the second portion of the class, and it will have essentially 3 parts, and you'll have a choice of which of those parts to do. So you can pick one of the 3. You can pick more than one if you like, but you're required to only do one. And we'll have one part on maximum entropy reinforcement learning, so this kind of control as inference stuff that we covered. We'll have one portion on exploration, and we'll have one portion on meta-learning. The maximum entropy RL and exploration will most likely come out tonight at midnight after homework 4 is done. The meta-learning will actually probably come out on Friday after the meta-learning lecture. And then we'll adjust the due date accordingly. It'll be the same due date for all of them, but you'll have at least 2 weeks after the meta-learning portion comes out. And then you can pick which one you want to do. So if you'd like to do the meta-learning one, then hang on until Friday. If you'd like to do maximum entropy RL or exploration, you can get started on that as soon as it comes out. So we'll make a Piazza post to explain all this shortly, but this is just for your information. Okay, so let's discuss the main material of today's lecture. So we'll continue where we left off last week. And last week we talked about how when we would like to learn in new settings more quickly, one of the things that we could do is we could actually transfer knowledge from previous tasks. So in much the same way that people don't really learn things entirely from scratch, they actually use their prior knowledge, their prior understanding of the world to learn every new task, we can develop reinforcement learning algorithms that can also make use of prior knowledge. And we broadly categorized methods for transfer into 3 categories. What I called forward transfer, which basically involves training on a particular task, which we call the source task, taking something from that source task, and then using it to more quickly solve a target task. And we just began talking about this last week, and we just talked about 1A, which is try and hope for the best. So sometimes if your source task and target task are similar enough, maybe things will just work. Today we're going to talk about how to go beyond that. We'll also talk about multitask transfer. So multitask transfer, maybe in some ways, is actually more representative of what we really think about when we say prior knowledge. Multitask transfer refers to the setting where you've solved many different tasks in the past, and your new target task is going to somehow be similar, or maybe it will come from the same distribution as those source tasks that you solved. And then on Friday, we'll have a lecture on multitask meta-learning, where we'll also have a multitask setting where you've solved many prior tasks in the past, but now your goal will not be to directly transfer a policy or a model from those tasks, but to actually transfer a learning procedure. Basically, how do you use your past experience of solving other learning tasks to solve new learning problems more quickly? And for this, we'll actually have a guest lecture on Friday by Chelsea Finn. I think it'll be great, and I would really encourage all of you to come to class and see the guest lecture on meta-learning. But today we'll talk about 1 and 2. And again, to reiterate this, I mentioned this last week as well, transfer learning is a very active area of research. There isn't a single solution that works for all transfer learning challenges. And these lectures are really going to be kind of a survey of recent papers to give you some idea of how people have approached this problem in the past. There isn't a single solution, but hopefully what I'll present today and what Chelsea will present on Friday will give you sort of a map of the landscape of transfer learning methods. Okay, so let's discuss forward transfer. At the end of the lecture last week, I began talking about fine-tuning. So fine-tuning is a very, very popular method of transfer in supervised learning. In fact, some people don't even call it fine-tuning, but some people don't even call it transfer. They just call it pre-training and fine-tuning, but it really is a transfer learning technique. So one of the most popular transfer learning techniques, in fact, in supervised learning is to take a big data set like ImageNet, train a big convolutional neural network to classify ImageNet. So ImageNet, for those of you that don't know, is a data set of images with semantic labels. And the full ImageNet data set is about 15 million images, but the canonical training set that everyone uses, which is also called ILS-VRC, is 1.5 million images, a subset of ImageNet that was selected for a visual classification challenge. So if you train a big convolutional network on ImageNet, because it's such a large, diverse data set with so many different classes and so many different images, you can actually take the features in that learned convolutional network and use them to solve new visual recognition tasks. And you could, for example, learn to classify parts of birds. And the reason this works, of course, is that ImageNet is a large and diverse data set that captures the kind of variability that you see in the visual world. So pre-training on ImageNet works very well, and you don't have to really do anything very fancy. You could just directly take the weights of your neural network and then train them some more on a new task with a relatively small amount of data, and actually oftentimes get a good result. So what's the equivalent of like ImageNet features for reinforcement learning? Is there something like that we can do in RL? Well, unfortunately, the simple answer is they don't exist. And they don't exist because of how RL problems are set up. So unlike something like ImageNet, which is a huge, very diverse data set, reinforcement learning tasks are generally less diverse. So if you trained the little ant to run forward, well, maybe you could say that running backward is somehow structurally similar to running forward. But it only really learned to run in one direction. So if it had learned to run, forward, left, right, up, down, and so on, maybe it could get some useful knowledge for running backward. But if it only learned to run forward, there just might not be enough variability to really help with fine-tuning to running in a new direction, let's say. So this makes the features less general. It makes the features inside the network much more narrowly tailored to the particular reinforcement learning tasks that they were trained on, and the policies and value functions become overly specialized. So even though they might contain some kind of structure that is similar to the structure you would need for a different task, it might be just too specialized to the single task that you trained it on. There's another more subtle but also very troubling problem, which is that if you have, sorry, this should be fully observed MDPs. So for fully observed MDPs, the optimal policies are deterministic. You can actually prove this. So if you have a fully observed MDP, there exists an optimal policy that is deterministic. There might also exist another optimal policy that is stochastic, but usually most reasonable reinforcement learning algorithms like policy gradient will actually recover a deterministic policy at convergence. And if you recover a deterministic policy at convergence, then what happens is you're losing the ability to explore. So you take your policy gradient algorithm, it has, let's say, a Gaussian distribution over continuous actions. Initially, the variance of that Gaussian is very large, but as it converges to the optimal solution for, let's say, running forward, the variance will shrink until it goes to almost zero, at which point this guy is going to be doing a very good job of running forward, but the resulting policy does a very poor job of exploring. So if you were to suddenly change the task objective, it would have a very hard time adapting to that because it has lost the ability to explore, because it has found the near optimal and near deterministic solution to this problem. So these kind of low entropy policies that you get after training on a particular task are then actually very poorly suited to adapting to new tasks because of the lack of exploration. So one of the things that we can do that will actually address both the entropy problem and to some degree the diversity problem is to make use of maximum entropy policies. So this is something that we actually learned about when we talked about control as inference. When we talked about control as inference, just to remind all of you, we had this graphical model where we say that, well, in addition to the states and actions, we'll add these optimality variables, whose probability of being true is proportional to the exponential of the reward. And we saw in the control as inference lecture that if you perform inference in this graphical model to figure out P of A given S comma O, that corresponds to something that's very similar to reinforcement learning. It corresponds to maximizing the expected reward, but also maximizing the entropy of the policy. And when you do this, you actually get two benefits that can make this very useful for transfer. The first and most obvious benefit is that because you're explicitly maximizing entropy, you are ending up with a policy that is not deterministic at convergence. So for those of you that don't remember from the control as inference lecture, the intuition behind this is you're essentially asking the policy to find a solution that has very high expected reward, but at the same time is kind of as noisy as possible. So be as random as you can be while still getting high reward. So if you're as random as you can be, your entropy will still be high, which means that you'll still be exploring. So if the reward changes, you'll be able to adapt to that. But perhaps more subtle is the fact that if you're maximizing entropy like this, you're basically asking the policy to solve the task not just in one way, but in all possible ways. Because if there's a task that it can solve in two different ways, and it solves it in both ways randomly, then we'll have larger entropy than if it only solves it in one way. So if you solve a task in all possible ways, you're getting more diversity out of a single task. And let me illustrate this with a diagram. Let's say that I have that little quadrupedal ant that I had before. I don't know why this thing is called an ant. It has only 4 legs, but for some reason everyone calls it an ant. If you want to solve this navigation problem, that you have to get to the blue X in this room that has a wall in the middle, right? There are 2 ways to get to the destination. You could either go up or you could go down. Going down is a little bit worse in terms of reward. It's a little bit longer, but only a little bit. So probably if you were to run regular reinforcement learning, you would get the solution shown here. You would go up and you would reach the target very quickly. But if you were to run maximum entropy reinforcement learning, depending on how the distances play out, you would probably have a policy that with somewhat high probability goes up and with somewhat lower probability goes down the other way. And now let's imagine a very simple transfer scenario. Let's say this is the source domain, and my target domain has a wall in it that blocks this passage. Now, if I had the deterministic policy that only goes up, that policy actually hasn't learned anything that is useful for solving the problem in the target domain, because in the target domain that passageway is invalid. But if I have a policy that even occasionally goes down, then that policy can adapt more efficiently to the target domain than one that is initialized from scratch. So maybe if it takes the lower passage 10% of the time, you generate 10 rollouts, one of them will actually see the reward. Whereas if you're taking the deterministic policy here, none of the rollouts will see reward. So this is an illustration of how maximizing entropy can actually increase diversity even for a single source task. So learning to solve a task in all possible ways basically provides for more robust transfer. And we can actually validate this experimentally. So this is actually some videos that I actually showed back when I talked about control as inference, but I'll show them again here just to emphasize the point. So there was this kind of creepy illustration of the ant learning to run with maximum entropy reinforcement learning with a reward function that doesn't tell it where to go. The reward function just tells it maximize the magnitude of your velocity. So if you ask it to maximize the magnitude of its velocity, over here you see the result for a deterministic policy. The deterministic policy has additive noise, but otherwise the policy itself is deterministic. And here you see the result for a maximum entropy algorithm. And you can see that the maximum entropy one generally runs in all possible directions, whereas the deterministic one runs in one direction, then because of the random noise it kind of falls over and gets a little more variability. But this, the one on the right, gets much wider coverage. And you know, what it's showing when the screen flips like this is that it's basically showing different random seeds. So the deterministic one picks a different direction for different random seeds, but within a single random seed, it has a single kind of direction it focuses on. So now what we can do is we can treat that thing as a source domain, and we can have a target domain where the ant now has to run in a particular direction. It has to run in a particular direction because there's some walls that constrain it. So here the goal now is to progress along this hallway as far as you can. And what you're seeing here, this is the learning from a random initialization. This is learning from a deterministic policy, trained over here. And this is learning from a stochastic maximum entropy policy trained over here. And again, the deterministic policy has additive noise, but the noise itself is not trained to achieve maximum coverage. It's just standard heuristic exploration noise, kind of the continuous version of epsilon greedy, essentially. So if we look at the learning progress, initially they're all doing something not too great because none of them actually know which way to go. But this policy that was initialized with maximum entropy, however, it has the knowledge of running in all possible directions, so it just has to specialize that knowledge to this one direction. Whereas the deterministic one has to essentially unlearn whatever direction it used to run in and relearn running in the right direction. And the random initialization just has to learn everything from scratch. So as learning progresses, over here you can see the epoch, it actually progresses further and faster. So this one gets further along the hallway for the same number of epoch. And you can look at this quantitatively too. So if you look at the graphs, the blue line here shows what happens with maximum entropy for different kinds of hallways. So the narrow hallway is what's being shown here. The orange shows what happens when initializing from scratch, and the green shows what happens when initialized from a deterministic policy with additive noise. So you can see that adding entropy does in fact improve transfer. Any questions about this? Okay, let's continue. So there are some issues with fine-tuning. Does anybody have any ideas about what issues we might have with fine-tuning? What might go wrong with fine-tuning? Any problems? What if we want to fine-tune with a very small amount of experience? Let's say we're doing off-policy learning, we're doing Q-learning, for instance, and we want to fine-tune using like 10 rollouts. What might go wrong? Anyone want to venture a guess? Yeah. You could overfit, yeah. So deep networks work best when they're very big, especially if you're learning from images, for example. Maybe you want to learn to play Atari games, use a big convolutional network. But when you fine-tune, you typically would like to use a small amount of experience, because if you were fine using a large amount of experience, you would just learn from scratch. So when you have a small amount of data and a big network, that's basically the recipe for overfitting. So while fine-tuning in practice can work quite well, there's still a limit to what it can do, because at the end of the day, you're training a large number of parameters on a small amount of data, which is a bad recipe to have. So perhaps we can figure out some way where when we fine-tune, we have like a small number of parameters that are being trained, but when we pre-train, we have a big network. So can we somehow get the benefit of both? Can we have a big network, but avoid this overfitting by only fine-tuning a small number of parameters? Can you elaborate on that a little bit?
You can pre-train your models layer by layer.
Mm-hmm.
For example, you can fix the other layers, only train the first layer. Then if the first layer is
Mm-hmm.
trained, you continue to the second, to the third, and to the end.
Right. So the answer for those that didn't hear is that, well, maybe you can train, let's say, only one layer. So you freeze them, or maybe you train it layer by layer. So you freeze all of them, train the first one, and then maybe you train the second one, something like that. So so the simplest version of this is just like fine-tune a few layers. Pick some small layers in your network and only fine-tune those, and don't let the others change. So if you're playing Enduro, let's say, you have your big convolutional network that actually processes the images. Then maybe you have a big fully connected layer, and then maybe you have a small fully connected layer, small relative to the rest of it. So maybe the whole network has perhaps 1 million parameters, but that small layer only has a couple hundred. Then what you could do is you could only fine-tune that layer. That's good, because now the number of parameters is much smaller. What might be a downside of doing that? Right. So the answer was the features in the convolutional tower might not be the right features. So maybe you pre-trained this thing on playing Pong, and now you're trying to play Enduro. well, the sprites in this game look completely different than Pong, so perhaps you just don't have the right features for it. So you have limited expressivity. You could let the gradients from this flow all the way into the rest of the tower, but then the big gradients at the beginning might wipe out the nice initialization down here. So you kind of lose out either way. So what you could do instead is you could take your big pre-trained network, and then you could add new layers for the new task. And those new layers can be smaller so that they don't overfit. So this is basically the idea behind something called progressive networks. You freeze the old layers so that you don't forget anything that you learned in your initialization. So this big error gradients wiping out your initialization is not an issue because we don't let these layers change. And then we add new layers that are small. So specifically, the way we would do this is, let's say we train on Enduro, and now we want to learn to play Breakout. We take this, the Enduro policy, and we freeze it. And then we're going to feed in the Breakout images into this convolutional stack and also into a smaller new convolutional stack. And then the fully connected layer here is going to get the input from both of them. So we're going to concatenate that. And this thing, the blue stuff now, is much smaller than the gray stuff if we don't want it to overfit. And we can just do this at every layer. At every layer, you put in the input from the previous layer of the new stack and the previous layer from the old stack. But the old stack is frozen. So all the stuff in gray is frozen and not allowed to change. And then at the end, you output the policy for the new game. So obviously, you can't do anything with this thing, but you can use just a new linear layer at the end to output the policy. So this is the basic idea behind progressive networks. Does anyone have any questions about how this works?
I think it seems like the origin network.
Right, so the comment was it kind of seems like it's learning the residual, so the intuition for that is that basically if this thing already outputs the right answer, then this thing doesn't really need to output anything. So this thing just needs to output the stuff that's missing from this, which is a valid interpretation of this thing. Any other questions? Yes?
Do they usually have the same number of layers, or you can actually make it smaller?
Yeah, so the question is, do they usually have the same number of layers? The answer is that it's up to you. So you could definitely skip a bunch of layers here. So you could have like one blue box here might correspond to like 5 gray boxes there. That's totally fine. I believe that in the paper they actually do match it layer by layer, but you don't have to. Yes, question back there?
So when you train your network in this way to sort of learn how to play new task, is the old network still good enough to play the old task?
Right, so and this is actually a very good question. The question was, when you do this stuff, is the old network still solving the old task? And in general, when we talk about transfer learning, sometimes we care a great deal about this question. Sometimes we don't care at all. This is sometimes referred to as the forgetting problem. So if you hear someone say forgetting in the context of transfer learning, what they mean is if you transfer from the source domain to the target domain, are you still doing well in the source domain? So fine-tuning, for example, good, interesting question there. Does fine-tuning actually prevent forgetting? Any ideas about that? Does fine-tuning prevent forgetting? No, it doesn't, right? Because when you fine-tune, all you care about is the target task. So with fine-tuning, you would lose the ability to do this. With this technique, you actually don't. So this old network hasn't changed at all. So it's still just as good at solving the source task as it was before. The new tower can't solve the source task at all. It has only been trained on the target task. Okay, so let's look at how well this works. So the answer to does it work is that it sort of works. So it prevents forgetting by construction, but as far as actually improving on fine-tuning, the results are actually a little bit mixed. So we can look at this comparison. It takes a little while to parse this fully, so let me explain what's going on here. There are 3 different classes of tasks, and for each task, they're showing the mean performance and the median performance as a percentage improvement over the first baseline, which I'll explain what that is in a second. And the 3 tasks are playing different variants of Pong. So this is like Pong oriented in different ways with paddles that are different sizes and so on. Transferring between different Atari games, and transferring between different first-person navigation tasks. And the baselines are the following. Baseline 1 is just train on the target domain from scratch. Baseline 2 is the thing that I described earlier, when you freeze the entire network and you only train the top layer, so you only fine-tune a few parameters. Baseline 3 is essentially fine-tuning everything. So you transfer the model from the source task and you fine-tune the whole thing. Baseline 4 is kind of a degenerate progressive network. It's saying, let's have the same architecture, the same number of parameters, but instead of transferring the left stack, we'll just initialize it randomly. So it's just a control just to make sure that the additional parameters over here aren't helping simply because they're parameters, but that there's actually transfer. And then the actual progressive network transfers the left stack and trains the right stack. And you can also transfer with multiple columns like this from multiple different prior tasks. So the results here are a little bit mixed. So if you look at, for example, the median column, like it helps a little bit on the Pong thing, but some of these baselines are actually very strong. So if you look at baseline 3 in particular, it kind of gets pretty close to the same value. Baseline 3 is the standard fine-tuning approach. So empirically, seems to improve a bit. Not that different from fine-tuning, but it's quite nice that essentially by construction, you're still able to solve the source task because you don't modify the previous weights. So that's kind of the outcome for that. And then in their evaluation, they also show this kind of pre-training on a simulated robot and then fine-tuning on a real robot. And again, it's kind of a little bit mixed. So here orange shows fine-tuning, and then the two blue lines show the progressive network. So it's a bit better, but doesn't seem to make an enormous difference. So it alleviates some of the issues with fine-tuning and conceptually has this kind of very elegant explanation, but it's also not entirely obvious how serious those issues are. So maybe this is not as big of a deal. If you care about forgetting, it's a much bigger deal. Okay, so a question.
You still have to prevent overfitting on the source task here, right? Because nothing has changed about the big network.
Right. So the question was, well, don't we still have to prevent overfitting on the source task? The answer is yes, but usually when we're dealing with transfer learning, we kind of assume that the source task there we can interact with the environment as much as we want. It's really the target task where we need to be efficient. That's not the only way to look at transfer learning, but typically when people talk about source and target, they sort of assume that in the source domain you have as much as you want. Okay, so summary of fine-tuning. You could just not do it, try it and hope for the best, which sometimes works. Like sometimes there's enough variability in the target domain that you just run the policy in the source domain and it just succeeds. That can happen. So if you're studying transfer, like try that first. You can do fine-tuning. There are a few issues with fine-tuning in RL that are a bit different than the issues with fine-tuning in supervised learning. So maximum entropy can help alleviate those issues. The two issues are that the entropy of the policy goes down, so you lose exploration. And the second issue is that you might not have enough diversity in the source domain. And then you can develop specialized architectures that are designed to make fine-tuning work better, which addresses some overfitting and expressivity problems essentially by construction, just because of how the network is set up. But what if we're allowed to actually manipulate the source domain? What if the source domain is not a fixed thing, but it's something that we actually choose? So we have some difficult target domain, and we get to actually choose a source domain from which to transfer to make transfer work well. So far, our source domain has been fixed, like maybe the source domain is the ant running around in the empty room, and the target domain is the ant running in the corridor. But sometimes we can actually design the source domain. This is the case, for example, if you want to transfer from simulation to the real world. If you want to train a policy in simulation, you get to pick which simulator you use, so it makes sense that you would pick the simulator that is best suited for transfer. But you probably can't pick it to be exactly the same as the target domain, because the target domain is very complex in some way, or maybe you don't know something about the target domain, so you can't have things match exactly. The idea for this setting is going to be actually very similar to the things we saw for fine-tuning. With fine-tuning, we saw that having more diverse source domains, for example, by maximizing entropy, can help transfer. In this setting, we're also going to try to create source domains that are as diverse as possible, but now we can actually do it by choosing the right source domain distribution. So let's go through a simple kind of physics example of this. Let's say we want to have the hopper which all of you are familiar with from homework 1. We want to have it hop, but our training hopper has the wrong mass. So maybe at test time, the hopper has maybe lost some weight. Now it's a little skinnier, and maybe our policy might not work anymore. So if you just train the hopper to hop with its normal mass, and then at test time it's a much lighter hopper, good chance that your policy won't work anymore because it needs to apply very different torques on the joints. So one idea that actually ends up working quite well, surprisingly well in fact, is instead of training for a single mass, what if we inject a lot of randomness into the mass of the hopper? We train a single policy that can control a heavy hopper, a light hopper, a medium weight hopper, and so on. So if we train one policy that works with all different weights of hoppers, then perhaps it'll work on a new weight that it hasn't seen before. This is kind of a non-trivial hypothesis because you could also imagine that it's very difficult to control hoppers with different weights, and maybe the policy would become very conservative and it would just do something very slow or very deliberate. So we can analyze this a little bit. What these graphs are showing, it takes a second to take this in. Each graph shows the performance of a policy trained for a single mass. This one is for a mass of 3, this one for a mass of 6, and this one for a mass of 9. And what it's showing is the performance of that policy for different masses at test time. So the x-axis is the test time mass, and the y-axis is the reward. So unsurprisingly, you can see that if you train with a mass of 3, it does very well for a mass of 3, does quite well for a mass of 4, and then kind of does pretty poorly once the mass gets to about 6. If you train for a mass of 6, does very well for a mass of 6, but poorly once it drops to about 5 or rises to about 8, right? And so on. So this is more or less what we expect. It turns out that if we train for a distribution of masses, this is actually the performance that we get. So this purple line is the performance for different masses. It's basically a horizontal line right there at the top performance. And the distribution of training masses is a bell curve, so it looks something like this. This is very interesting because for those of you that are familiar with robust control, you might recognize this idea. In robust control, this is a kind of a very old idea. You introduce perturbations into the training process, and what you typically get in robust control is controllers that are conservative. They'll perform the task, but they'll perform it at a lower level of proficiency because they're trying to hedge their bets against all possible dynamic systems. The nice thing about deep networks is that because they're so expressive, they can actually represent strategies that succeed for multiple different models. This would not work every time because you could have settings where the physics are just so different that there is no single policy that works, and we'll see later on how we can actually address that issue also. But for many simpler problems, simply randomizing the environment can be extremely effective. Question?
So you're training with randomized physical parameters. Is the policy actually aware that the mass has changed, or is the environment
Yeah,
changing?
this is a very good question. So the question was, is the policy actually aware that the mass is changing? In this work, no. In this work, it's exactly the kind of policies, the standard neural net policies that you guys trained with for homework 1 or for homework 2, only here they're just trained on different environment. Later on, we'll see how you can actually get even better results by incorporating some of that knowledge. Any other questions? Yes?
You mentioned ImageNet. Is this similar to like data augmentation in computer vision?
Yeah, that's a really good comment, yeah. So in computer vision, for those of you that aren't familiar, a very standard technique to improve generalization of classifiers, for example, is to take your data and then computationally modify it. So you could, for example, take all of your photographs and add random changes in brightness or random changes in hue. So this is a very similar idea to data augmentation in computer vision, and it can actually give you big improvements in robustness. One very non-trivial question to ask about this kind of technique is, well, okay, it can do well when the mass changes because we trained it for different masses. But in reality, transfer can be hard because the thing that changes in the target domain is something that we could not change in the source domain. So maybe your physics simulator doesn't model some phenomenon that actually happens in reality. Maybe your physics simulator doesn't model the effect of like air resistance on the hopper as it's hopping at really fast speed or something like that. So one of the things that we can do is we can look at the effect of unmodeled phenomena. And the unmodeled phenomena here specifically was the friction against the foot of the hopper. For unmodeled phenomena, it turns out that actually things work better when using randomization than when identifying the model with maximum likelihood. So what you can do is you can take your model, which does your physics simulator, which doesn't allow you to vary the ground friction. You can take data from the real system, which has different ground friction, and you can try to figure out what is the parameter of the simulator that most accurately resembles reality. So that's the maximum likelihood line here, the green line. Or you could instead take the parameters of the simulator and randomize them. The simulator will make predictions that match the real world less accurately, but when you have these unmodeled phenomena, that can actually be better. Because why? Well, because when ground friction changes, the actual outcome of that is kind of similar to having a lighter hopper. Lower friction, lower mass kind of results in roughly the same forces. So if the unmodeled phenomena actually, in some sense can be reflected by changing the phenomena that are modeled, you can actually get robustness to those as well. Of course, there's no guarantee here, because if the unmodeled phenomena is something like, oh, sometimes there's a pit in the ground and the hopper falls in and dies or something, if you don't have the pit there, then you can't prepare for it. So it kind of depends, of course, on how diverse your simulator is. Okay, but let's now talk about the other point, the one that Murtaza raised, which is, can we actually add some knowledge of the physics of the variability between models into the system to get better results? And that's actually the idea in this paper called Preparing for the Unknown. So the idea here is that we'll also train on a diverse set of different physical environments, but now we'll actually separate our policy into two parts. This part labeled UP, this is a policy that maps from your state to your action, but it also takes as input a little context mu. And that context is calculated by another network, actually a recurrent neural network, that looks at a past history of states and actions. Because if you look at a past history of states and actions, you can kind of guess what the physics are. So if you saw that you applied a big force, but the hopper moved very little, then perhaps it's very heavy. If you applied a big force and it moved a lot, then perhaps it's very light. So this box labeled OSI is actually trained to predict those physics parameters. In this particular work, they actually give it the ground truth physics parameters during training, so they have a little vector that describes the setting for the simulator. They train this model to predict those settings, and then at test time, they have a new target domain where they do not know the ground truth settings, but they just run this recurrent neural net, get the corresponding context, feed it into their policy, and have the policy act. And they can get their hopper, which looks different for some reason, to hop with larger variability in the physical parameters. So here what they're doing is they're changing the center of mass artificially. So the center of mass of the hopper is somewhere here, and they're shifting it backward or forward and trying to measure robustness to that. So their method is shown in red, and the green line shows the method that gets the ground truth physical parameters. So this illustrates that you can actually use these recurrent networks to do a kind of learned system identification, essentially, directly at runtime as you're executing in the target domain. Question?
Would it be common for a policy like this to sort of have like a warm-up, sort of like feel out the environment before?
Yeah, so the question was, well, should you have like a little warm-up phase? If you're trying to identify your physical parameters, should you kind of experiment a little bit, figure out what's going on, and then act? One would think that the answer is yes, but in this case, it's actually so simple to identify the relevant parameters that you don't actually see that warm-up phase. So it basically starts right away, just from a few time steps. And this is actually fairly typical. The reason for that is that it's important to remember for these policies, they're not trying to do everything. They're trying to do a particular task. So the amount of interaction that you need to identify the parameters well enough to do your task is much lower than the amount of time that you need to identify your parameters with high precision. So you don't really care about what the mass is. You just care about it insofar as it'll let you take the right action. So in fact, one paper that takes this idea to the extreme is this paper by Shrub and Peng called Sim-to-Real Transfer of Robotic Control with Dynamic Randomization, where what they do is they actually take an approach similar to this, except they don't even supervise the RNN part. So the RNN is not actually supervised to output the real physical parameters. It just outputs some RNN hidden state, and the whole thing is just optimized end-to-end on the reward on a large set of simulated training tasks. And then what they experiment with is whether you can train a robot to push this object across the table in different simulators, and then use this RNN approach to generalize to real-world robots. Okay, any questions about this kind of randomization and system identification idea? Question back there.
If you pre-train, I don't know, either a net or a Python call to like a Dijkstra or a star kind of algorithm that's programmed in efficiently,
Mm-hmm.
can you learn to map real-world problems to those sorts of?
Yeah, that's an interesting question. So the question was, if you have some procedure that solves, let's say, a search problem or a planning problem, can you actually train a network to help utilize that? The answer is yes, you can. We actually probably won't cover it in this class this year, but there was a guest lecture last year from Aviv Tamar that talks about exactly this problem using something called value iteration networks. They're actually neural networks that embed model-based value iteration and then train the network to utilize that as a subroutine. So for that, you should check out last year's videos by Aviv Tamar. Okay. Now let's also talk about how we can take this idea to the world of vision-based control. So if you're doing vision-based control, then transfer from simulation to the real world becomes even harder because simulating realistic visual appearance, especially in a way that reflects real-world statistics, can be difficult. And in fact, what's realistic to a neural network might not be the same as what's realistic to us. So we might look at a computer-generated image and say, oh, this looks very realistic. But in fact, maybe that computer-generated image has all the walls be exactly the same color. We don't care about that because we don't fixate on such things. But a neural network trained in that environment will become quite confused if the color of the wall suddenly changes. And this often happens with procedurally generated images, that if you're not careful and you don't create natural statistics, you might get images that look realistic but have these kind of pathological irregularities. So an interesting question to ask is, though, if we're going to train in simulation for vision-based control, how should we design our simulator? Should we try to make it very realistic, or should we instead try to make it very diverse? And it turns out that if you make your simulator very diverse, you can actually get away with fairly unrealistic simulators. So this is a technique that's also called domain randomization. The idea is that you don't necessarily need to render, let's say you want this quadrotor to fly through hallways. You don't necessarily need to render out the hallway very realistically, but you need to render out a huge variety of hallways that don't have these pathological regularities. So if you actually look at these things, some of them look a bit silly, like, there's like concrete and brick in the same building, there's some, yellow stuff on the wall, like not necessarily realistic textures, but highly varied textures. So this is an illustration of some simulated environments in this project called Cat2RL. And the idea was, let's use these highly diverse but not necessarily realistic simulations to train a policy for a quadrotor to fly through hallways. And if you do this, you actually get fairly decent flight in hallways. So the red dot is indicating where the vehicle chose to fly at any given time. But you can actually still get in trouble if you have some phenomena in the real world that were missing in the simulation. So for example, if your simulation didn't have any reflective surfaces or glass, then you can get your quadrotor flying into reflective surfaces on glass. But overall, with enough variability, you can see that there's some decent generalization. And this idea has been applied quite widely for things like pose localization, robotic manipulation, and so on. So in general, for perception-based tasks, if you get to choose the distribution of source domains, choosing to randomize it can be a really good idea to enable effective transfer. Okay, now, so far, we're still talking about transfer where you just design your source domain, you don't have any data from the target domain, and you just need to design those source domains so that they transfer effectively. In reality, you might have a little bit of additional experience from the target domain while you're still interacting with the source domain. So you can actually change how you train on the source domain using a little bit of target domain data. And this is basically the idea behind domain adaptation. So you can do a bit better if you use that. So far we talked about pure zero-shot transfer, which means you learn the source domain so that you can succeed in an unknown target domain. In general, this is like not a well-defined problem, because if the target domain differs from the source domain in some unexpected way, there might be nothing that you can do, right? So as I mentioned with the hopper, like, if there's suddenly a pit of death in the target domain and there's no pit of death in the source domain, there's just nothing you can do to prepare for that. So what if, let's restrict ourselves for now to the setting of image-based control. And let's say, well, what if we saw a few images of the target domain? So what if we saw something about what the statistics of the observations in the target domain look like? Well, it turns out that we can do better if we have access to a little bit of target domain data. So let's say that we have our simulation, and then we also actually saw a few photographs in the real world, something like that. So one of the things we can do is we can employ techniques for domain adaptation. Domain adaptation is something that has been studied quite a bit in fields like computer vision to transfer data across different data sets. And you can use the same idea in reinforcement learning. So you could, for example, say, well, maybe we're getting this robot to learn how to hang something on a hook for this grocery scale, and we have some simulated images that are not very realistic, but in some structural way they're similar. So in the real world, there's a grocery scale, and you have to hang your rope on that. In the simulated image, there's just some like white circle. So you can if you understand that this white circle matches the grocery scale, then you can put those things in correspondence and actually use your simulation. But visually, they look very different. So what you could do is you could say, well, we don't need our images to look realistic to the neural network. We just need, or we don't need them to look realistic to us. We just need them to look realistic to the neural network. We need to change our network so that it basically can't tell the difference. And this is sometimes referred to as adversarial domain adaptation or domain confusion. What you do is you take your network, you give it the real images, and you give it the synthetic images, and then you put in a little loss, it's labeled as the confusion loss here, that basically says, I would like the error for a classifier that is trying to guess whether it's looking at a real image or a fake image to be high. So this confusion loss comes from a classifier that is trained to classify from looking at the features inside the network, whether these are features for a real image or a fake image. And the network is trained essentially to fool that classifier. So it's not trying to actually modify the images. It's just trying to learn features from which it is impossible to figure out which domain you're in. And of course, if you can learn features like that, if you can learn features that are statistically the same from looking at this as they are from looking at this, then those features have to put the two images into correspondence. So this is the idea behind adversarial domain adaptation. You could also actually directly modify the images. You could actually go in and take the synthesized images and literally change the pixels to make them look more realistic. And that corresponds to a generative adversarial network. At that point, your classifier is again trying to guess real versus fake, and then you have another image modifier network that goes in and actually modifies the image. So that's the idea in the next work that I'm going to show. There's actually now a dedicated image translation network, which is basically a GAN that looks at synthetic images and tries to turn them into real images. And then there's going to be a separate policy that is trained on transformed synthetic images and real images. This is a bit more involved because training this GAN can be quite complicated, but it's a little bit more interpretable because you can actually look at the generated pictures. So in the video I'm going to show you next, this idea is applied to a robotic grasping task, and we'll actually see the generated pictures. So this is the simulation. It's kind of looks like a video game from the 1990s. And this is actually that same simulated sequence, but translated into realistic images. And here you can see it's split half and half. So it kind of makes the robot look a little blurry, but also a little bit more realistic, and makes the objects into kind of more realistic looking shapes. So if you do this, you can also get a big improvement in the sample efficiency in the target domain. Okay, so let's summarize our discussion of forward transfer. We talked about pre-training and fine-tuning. We talked about how standard fine-tuning with RL is difficult, but we have some solutions. We talked about how we can modify the source domain, where basically randomization can help you a whole lot, and randomization can help with zero-shot transfer. And then if you have some target domain data, you can do domain adaptation, or you can even directly go in and modify the source domain observations via another neural network that tries to make them look more like the target domain. Okay, some suggested readings if you want to learn more about this. So this is the paper I discussed about fine-tuning. This is the progressive networks paper. This is the paper with the hopper, learning to transfer different masses. And this is the randomization for quadrotor flight. This is another randomization paper. And then this is the paper with the domain adaptation loss. And this is the one with the image translation. So these will be in the lecture slides, which I'll post on the website shortly. Okay, let's take a 3-minute break. And when we come back, we'll talk about multitask learning. So we'll be back at 11:01.
The method cross entropy, it just, I think it wants to find if this is function. It wants to find, for example, the minimum of this function.
Okay.
So he generates a big Gaussian, then he pick the elite, then
Yes.
go to here, and the standard deviation is going to small and small, so it picked this point, right?
Yes.
I think we can choose a more clever like E to this one.
You mean as the distribution?
Yeah. This
Yeah.
can be
So
better.
there is actually quite a bit of work on using different distributions for cross-entropy method. And you can use any distribution class you like. So the way the algorithm is actually defined is you generate samples, select the elites, and then train a distribution from your distribution class.
Yeah, because this distribution will let the difference between the values much larger.
Mm-hmm. Yeah, absolutely.
But I do not know how to implement this, because if you pick the elites for the Gaussian, you just estimate the mean and the Gaussian.
Right. So you have to have some way to efficiently perform maximum likelihood estimation for your distribution class. I mean, you could do it with like gradient descent, but then you get a very computationally expensive algorithm.
Yeah. And another thing is in computer vision, the adversarial attack is you can change a pixel, then you fool the classifier, right?
Mm-hmm.
Is it also the issues in IR?
There's a little bit of research in reinforcement learning on that. So there's some work you can look up by Sandy Huang. She's actually a student here at Berkeley who's studied adversarial attacks against reinforcement learning agents. So yes, it's possible. It's a little bit more involved just because the optimization that the RL agent is solving is more complex. Yeah. So figuring out how to attack it is also more complex, but it's possible.
That means computer vision based IR. So if
yeah. So her work is actually for Atari games. So she actually goes in and modifies the Atari image to fool the RL agent.
Okay, thank you.
All right, let's continue. So before the break, we talked about forward transfer. Forward transfer where you train on one task and then transfer to a new task. Although the definition of one task was sort of stretched a little bit when I talked about randomization. You could argue that randomization is actually many tasks, but it's kind of one task modified in random ways. But now we'll really get more into true multitask transfer, where your goal is to train on many tasks and somehow synthesize knowledge from that collection of tasks to generalize, hopefully, to new tasks that are different, quite different from any one of the tasks you trained on. And we'll discuss a few different ways to do this. So far what we saw is that essentially the more diversity that we have in the source domain, the better our transfer will work. But we saw that we need to either modify our algorithm or somehow build this diversity into our source domain with randomization. So for example, for simulation real-world transfer, we need to randomize the simulator. So if we can transfer from multiple different tasks, in some sense that diversity might come for free just because across many different tasks, your policy needs to figure out commonalities which will hopefully allow to generalize to new tasks that are from the same distribution but quite distinct from any of the ones you trained on. So in a sense, this is kind of closer to what people do, because when people learn a new skill, they kind of build on a lifetime of experience, not just on a single task that they did before. But it's substantially harder, because the previous tasks might not directly tell us how to solve the task in the target domain. So one thing we could imagine doing is saying, well, perhaps we need to just pick the knowledge to transfer that all these tasks are going to have in common. So if all these tasks sort of exist in the same physical world, perhaps the laws of physics are the same, so we can learn something about physics from our many source tasks and then transfer that to a target domain, which essentially amounts to saying let's do model-based reinforcement learning. So if the past tasks are all different, what they have in common is the laws of physics. So maybe you have the same robot doing different chores, or you have the same car driving to different destinations, or you're trying to accomplish different things in the same kind of open-ended video game. So the simple version of this is you can train a model on all the past tasks and then just use that model to solve new tasks. Just do it with your favorite model-based RL algorithm. And this is actually a fairly decent idea. Like, this will, in some cases, work pretty well. This is, in some sense, the multitask analog to try it and hope for the best. But a more complex version would be to train your model on many source tasks and then actually adapt or fine-tune that model to new tasks. And this can work even better, because now if your target domain is in some systematic way a little bit different, then that additional adaptation or fine-tuning will fix up your model. And if it's similar, then your model might work right out of the box. So it's potentially easier than fine-tuning the policy because if the task is very different, but the physics are mostly the same, the policy might not transfer. Like if the reward function changed, but the dynamics stayed the same, the policy would be really confused, but the model would be just fine. So let me give you one quick example of this idea in action. Here, the idea is to train a robot to perform some assembly tasks with one trial of that task, but using data from many prior assembly tasks. So the experiments here are kind of one-shot cross-validation style experiments. So there are many different assembly tasks, and when you see a video of the robot doing one of those tasks, let's say it's doing this little nail insertion thing, what you're actually seeing is a model that was trained on all the other tasks, and then it's just performing its first trial on the target task. So how can we do this? Well, the simplest way to do it is to just train a model on all the source tasks, and then just use that model with model-based RL to perform the target task. But if the target task changes in some systematic way, we can do an even better job of by treating that past model as a prior, and then using a little bit of recent experience, either to fine-tune that model or actually combine it in some Bayesian way with this prior, which is actually what you'll see in the videos that I'll show in a second. So there, it actually uses this as a prior for a Bayesian linear regression approach to estimate local linear models. But you can also do fine-tuning or many other ways to combine small amounts of recent experience with large amounts of past experience distilled into a model. So here's the video of that in action. You can see that the robot doesn't do this task very quickly because it does need a little bit of that experience to fine-tune the model appropriately, but generally does a decent job on tasks that it hasn't seen before. So you can see it's kind of feeling out this object to figure out roughly how the pieces fit, but then is able to do it once the model adapts enough. So that's the basic idea for model-based multitask transfer. Now another thing you could think about is, well, let's do the model-free RL, and let's think about ways that we can use model-free RL to learn multiple tasks all at once. So sometimes learning a model is very hard. Maybe you have very complex dynamics, you have really complicated images, and you'd really prefer a model-free approach. So can we learn a multitask policy with model-free RL that simultaneously performs many tasks and hopefully therefore generalizes to new tasks? So you have to kind of simultaneously transfer from multiple tasks all at once. One idea, a very, very simple idea, which is mathematically valid but very difficult to use in practice, is to actually take your many source tasks and construct a joint MDP. So you can actually, anytime you have many tasks, you can turn them into one really big task. And the way that you do that is you basically define your new joint MDP as an MDP where the initial state distribution is random, and there's a little bit added to the state that determines which task you're doing. You might not even show this bit to your policy. You can say, okay, the policy has to deal without it. The policy has to do it just by looking at the observations, but that implicit bit sort of encodes which MDP you're in. So in a standard MDP, you sample a state from P of S0, that gives you S0, and then you use your policy and you perform the rollout. In this kind of multitask MDP, P of S0 actually determines which of the source MDPs you fall into. So it's basically a way to turn multiple MDPs into one MDP. The initial state distribution determines which MDP you fall into, and you choose a different MDP randomly for every single rollout. So you just do that at the first state, and then you commit to that MDP for the rest of the rollout. That is a mathematically sound way to train a multitask policy with model-free RL. Part of why it might not work very well is that for most reinforcement learning algorithms, this will produce very high variance gradients because you have a lot of variability in these initial states. So if maybe your different MDPs are different Atari games and you're doing policy gradient, you might be computing your gradient from, let's say, 20 rollouts, each of which came from a different game. So the variance for that estimate will be extremely high. So a different idea, which you can view at a very mathematical level as essentially a variance reduction trick, but a rather elaborate one, is to actually train on each MDP separately and then somehow combine the policies into one. And in practice, this can work a lot better, especially when the different MDPs in your source domain distribution are very different from each other. So what I'm going to describe next is based on two papers, one called Policy Distillation and the other called Actor Mimic. And these papers came out at around the same time. I'll actually focus more on Actor Mimic just because it's a little easier to explain, but the idea is basically the same. So before I explain how we do this in RL, let me just, as a brief aside, introduce the idea of distillation in deep learning. This is in the context of supervised learning problems, and then we'll apply this idea to reinforcement learning problems. So here's a little bit of motivation. There's other motivation too, but this motivation makes a lot of sense. If you want to do really well at some supervised learning problem, maybe you want to win like a Kaggle competition or something, training a single model is often not the best way to go. You can often, if you have a learning algorithm, you can take that learning algorithm and use it to train an ensemble of models, and you'll probably do better than using a single model. This is true for deep nets, it's true for SVMs, it's true for just about anything. So this is actually how most ML competitions are won, by taking some decent learning algorithm and then making an ensemble of it. But it's very expensive. The larger the ensemble, the better you do, but if you have deep nets and you have an ensemble like 100 deep nets, that's very, very expensive to use. So one thing you could do is you could say, well, now that I've trained my ensemble of deep nets, can I somehow distill the knowledge contained in that ensemble into a single network that'll be more efficient to evaluate at test time? And it turns out that you can do this, and it actually works very well. So what you do is you take your training set, and you're going to train your single small model on that training set, but you're actually not going to use the ground truth labels. What you're going to use are the probabilities, the class probabilities from your ensemble. So instead of using true class labels, you actually assign soft labels. Basically, every data point has some probability of belonging to each class, and the probability is averaged over the ensemble. So you take the ensemble's logits, you sum them together, and maybe you divide them by some temperature if you want to smooth them out even more, and then get probabilities from that. This is a little bit weird. We might ask, well, why is this a reasonable idea? Like, what is it that the ensemble labels tell us that the true labels don't? It seems like if we're not using the true labels, we're actually like discarding some knowledge. So the intuition is that there's actually more knowledge about the underlying structure in the data in the soft labels than in the hard labels. If you assume that your ensemble did a very good job of classifying the data set, which it probably did because it's an ensemble, it might figure out that sometimes the true label doesn't tell the whole story. Let's look at this picture. These are MNIST digits. These are handwritten digits. It's a classification task. And handwritten digits, you know, they all belong, each digit belongs to some class. It's a number between 0 and 9. But handwritten digits can be ambiguous. This is a 4, but it kind of looks like a 1. So the ground truth label for this digit is 4, but your ensemble will tell you that this digit has maybe a probability of 0.6 of being a 4 and 0.4 of being a 1. So when you use the soft label, you're actually learning that this is a digit that is probably a 4, but also maybe looks a little bit like a 1. So that teaches you more about what 1s might look like. Or maybe like one of these 6s kind of looks like a 0. I mean, these are actually pretty good 6s. But you can have a sloppy 6 that looks a little bit like a 0. And then again, you'd have a soft label that says this has like some non-trivial percentage chance of being a 0. And then you learn more about zeros from looking at that 6. So there's actually this knowledge about the structure, about the similarities between the classes that's embedded in the ensemble that you can distill out by doing this procedure. So in much the same way, we're going to be doing distillation on an ensemble of policies, except now these policies will be trained on different tasks. So they'll actually have different knowledge. So for multitask transfer, the general scheme is that we'll learn a separate policy, pi subscript e, on different tasks. Maybe we learn one policy for playing Space Invaders, one policy for playing Pong, and so on. And then we'll use the same distillation procedure to distill all of these policies together into a single policy that can play all of the games. So the loss function for the single policy is essentially a supervised loss function. But it's a supervised loss function that doesn't just try to classify into a ground truth action. It actually uses the probabilities of the actions assigned by the different policies in the ensemble. So perhaps for playing the game of Space Invaders, our loss is the log probability of each action weighted by the probability that that action would have been taken by the Space Invaders policy. If these probabilities are always 1s and 0s, then you're just doing regular supervised learning, and if they're probabilities, then you're doing distillation. So that's basically the idea. Yes?
So different tasks have the same dimension for the action and the state.
Right, so the question was, well, doesn't this require every task to have the same dimension for the action and the state? The answer is yes. So if you want to distill everything into one neural network like this, you do need the inputs and the outputs to have the same size. We'll actually describe a method towards the end of this lecture that lifts this restriction. Yes?
Isn't this distillation procedure only trying to like make one possible solve the same task you had at training time? Like this doesn't seem to be
Right. So the question is, well, is this even transfer learning? Because it doesn't seem to be transferring anything. We'll see actually the transfer learning results on the next slide. But there are a few ways that transfer can happen here. First, let's say that I don't have 4 games, but I have 10 billion games or something, right? Now, there's only so many ways to build a video game. So perhaps if you learn to play 10 billion games, then you can, then the policy that you get from that will generalize to a new game. Another thing you could do is you could say, well, okay, maybe it won't just generalize. Maybe I don't have 10 billion games. Maybe I only have like 10 games. But perhaps that policy can then be a really good initialization for fine-tuning on an 11th game. Question?
You need to make sure that the actions actually mean roughly the same thing across the games.
Yeah, this is an interesting question. So do you need to make sure that the actions mean the same thing across the games? Probably, but they clearly don't. And this is actually part of why it's difficult to use the single MDP method I described on the previous slide, is that sometimes, especially for Atari games, the tasks really don't have very much in common. So if you use a big enough network and you run this procedure, you will learn to solve all the games. It's just that potentially this network will learn something very silly. It will say, oh, let's look at the image. Let's look at whether the background is blue. If it's blue, use the sequest part of the network. And if it's black, use the breakout part of the network. That's a valid solution to the problem. So so while you don't need to make sure that the actions are in rigid correspondence, it's sort of up in the air as to how much sharing across games you'll actually get. Okay, so the procedure is basically analogous to what we discussed before for model-based RL, which was guided policy search. So it's this idea that you take multiple local solutions that solve some piece of the problem, and then you just distill them down into a single policy that solves the whole problem. Except that here, instead of the different local solutions being different initial states, here the different local solutions are different tasks.
When you distill them, which task do you choose?
So you actually do it, you average over all of them. So for every one of these policies, pi subscript EI, you take the data that that policy has collected and train the distilled policy on that. And then you average over all the tasks.
You use all the policy, but you have to choose one specific task to perform your distill, right?
So you take data that, you basically take a buffer that contains data from all of the policies, and the labels are these soft labels from the corresponding policy. Yes, question?
Is the final result really as good as each individual specialized agent?
Yes, let's look at that. The answer is no, it isn't. So you pay a little price, and the price that you pay is not nearly as large as if you were to train a single agent with RL on all the tasks. So the distillation does make it a lot better. Actually the answer to the particular question you asked is actually in the paper. This is showing something a little different. This is showing transfer to new games. So, but the answer to your question is you lose a little bit, not very much, especially if you use a big enough network. When you transfer to new games, the story is a little mixed. So what you're seeing here, the important lines to look at are the red line and the blue line. The red line shows learning from scratch on a new game. The blue line shows initializing from a policy trained on a bunch of other games. And on some games, you can see it helps a lot. Like on boxing, for example, the blue line starts off pretty high. On Pong, it helps a bit. But then on some games like Sequest, it doesn't help very much. And part of the reason for this, of course, is that the distribution over tasks is fairly complex. So different games are not necessarily going to have a lot in common. But something is kind of sometimes working. That's basically the story there. In general, though, this also highlights an important issue with multitask transfer learning and reinforcement learning, which is that you have to be a little bit careful about which tasks you experiment with. So if you're designing a new transfer learning algorithm, choosing the right tasks to experiment with is tremendously important, because if your tasks don't actually have a lot in common, you might have a very good method, but just not be able to understand that because there's no transfer that's possible from those tasks. Okay, now let's say that you distill all these different tasks into a single policy. An interesting question we could ask is, well, how does the policy actually know what to do? Like, how does it know whether it's supposed to be shooting the fish in Sequest or dodging the cars in Enduro? Well, so far in the games, it's basically apparent from the input. Like, you look at the screen and you can tell whether you're playing Sequest or Enduro because they look different. But that's not the case for all multitask scenarios. So what if the policy needs to do multiple things in the same environment? Maybe your different tasks all involve controlling the same robot, but sometimes the robot needs to do the laundry, and sometimes it needs to go and do the dishes. And you don't want it to mix those up because dishes won't get very clean in the laundry machine, and laundry won't get very clean in the dishwasher. So in that case, there's a very simple trick that you can use to basically turn this setting into this setting, where the task is apparent from the input. And that's referred to as contextual policies. So we can say that in this task, there's some additional context, which is what you're supposed to be doing. There's a context omega-1 for dishes and omega-2 for laundry. And instead of training a standard policy that predicts an action condition on a state, you train a contextual policy that predicts an action condition on a state and a context. It's a very simple idea. The context just tells you which task you're supposed to do. And this is exactly equivalent to a regular RL problem where you've simply modified the state space to concatenate the context at the bottom. So you're just solving a problem with a different state space where the context is now added to the state. This is a very simple idea, but it's actually tremendously useful. And it's been used in a number of different works, especially in robotics. You know, if you want a robot to learn to stack Lego blocks in different locations, the context is the desired Lego block location. If you want a robot to walk in different directions, the context is the direction that you want it to walk in. If you wanted to hit a puck with a hockey stick to a different direction, to a different location, omega is the destination where you want the puck to go. So contextual policies, very simple idea, a very effective idea. And as we'll actually see on Friday, it actually comes up very often in the context of meta-learning also. So you'll learn about contextual policies as a building block towards meta-learning later on. Okay, the last topic I want to talk about today is the design of architectures for multitask transfer. So when we talk about forward transfer, we saw that we could choose special architectures, namely progressive networks, that could facilitate forward transfer. There are interesting architectures that we can choose to facilitate multitask transfer as well. And this will actually address the question that was asked earlier about how we can handle different size inputs and different size outputs. So far, when we talked about multitask learning, we saw that at the end, we always end up with one network that can basically do everything. But what if some of our tasks in our multitask kind of task distribution have parts that are shared and other parts that are distinct? So for example, maybe your different tasks correspond to two different cars, one of which needs to drive using a camera and the other needs to drive using LiDAR. Now clearly you can't just feed your LiDAR observations into a network trained for image observations. They're not even the same size. But somehow driving has a lot in common, so there should be something that's shared. And maybe some of these cars need to drive in different cities. So you can clearly transfer knowledge for driving in one city using LiDAR to driving in that same city using cameras if you understand something about what cameras and LiDAR have in common. Another example, maybe you have 10 different robots that are trying to do 10 different tasks. Perhaps you can have 5 of the robots attempt one task, 5 of the robots attempt another task, and then another subset of 5 attempt a third task, and then transfer knowledge between them. Different robots might have different observations and different inputs, but something across the tasks should be shared. So perhaps what we can do is we can design architectures with reusable components. The whole network will not actually be transferred across all the tasks, but parts of the network will be transferred across subsets of the tasks. So this is the idea behind modular policies. The idea is that perhaps we have these cars with LiDAR and cameras, or maybe we have cars driving in different cities. So maybe we take our policy network and we split it into parts. Maybe we split it into 2 parts. So the first part deals with the observation, and the second part deals with the city that the car is driving in. So we have, for all the cars that are using cameras, they share the same first part, but for different cities, they have a different second part. And for all the cars that are driving within the same city, but with different sensors, they might have different first parts, but have the same second part. So let me make this a little more concrete. So in this example, we'll actually have multiple robots doing multiple tasks. Maybe you have a robot that needs to open a drawer, a robot that needs to push some big heavy object, and so on. And then the robots themselves are different. Maybe one robot has 3 links, another robot has 4 links, right? So what we could do is we could say, well, we take the cross product of these things, and there are 4 different tasks. In reality, you probably want a lot more than 4, but this is just for illustrative purposes. So there's 4 different tasks. And instead of having your policy mapped directly from the state to the action, it'll have a little task-specific part and a little robot-specific part. And every time you're using the 3-link robot, the first part of the network is the green piece. and every time you're using the 4-link robot, the first part is the blue piece. And every time you're opening the drawer, the second part is the yellow piece, and every time you're pushing the block, the second part is the orange piece. Crucially, we're not telling these pieces what it is that they're supposed to output, except at the very end where we get the usual reinforcement learning gradient. So what it is that the task network actually sends to the robot network is entirely up to the network. But because they all have to be trained together to succeed with many different possible combinations, they have to sort of develop a common language. So in order for a network to be, for all these pieces to solve all these tasks, they have to transmit something. The task-specific part has to transmit something that any robot-specific part can comprehend. Now, in reality, you can get a little bit of overfitting. You can get a situation where essentially the task-specific part outputs like 3 different things, one thing for robot 1, one thing for robot 2, and one thing for robot 3. So in practice, what you often have to do with these kind of modular network designs is regularize the bottleneck in some way to make sure that it's not allowed to transmit too much information. And there are a few different ways to perform this regularization. You could simply limit its dimensionality, which can be a very effective way to do this. You could also impose information theoretic regularizers like the ones that we learned about when we talked about variational autoencoders. So you can actually put a little loss on that bottleneck and make it a random variable, and then the loss says, well, that random variable should have low KL divergence against a prior. This is sometimes referred to as variational information bottleneck. But just limiting dimensionality can also work very well. And that's actually what's going to be done in the result that I'm going to show on the next slide. So, of course, in practice, we wouldn't train on all possible combinations. What we'd want to do, we might have a lot more robots and a lot more tasks, but we have 100 robots and 100 tasks. We'll train on some of the combinations, and then if we train on enough combinations, then this will generalize to new combinations that were previously not seen, which means that maybe the 4-link robot can perform the pushing task without ever having actually seen it, because the 4-link robot has done other tasks and other robots have done the pushing task. So here's a little simulated illustration of this for a slightly larger matrix. Of course, it works better if you have more tasks and more robots, but here, just for illustration, we have a robot with 3 links, a robot with 3 links that are of different length, and a robot with 4 links. And the robots might be reaching for a little white square, pushing a little white square to a red target, or inserting a little peg into a hole. So here's an illustration of what happens if you run the 4-link robot with the pushing task, which is the combination that was never trained before. And sometimes it works and sometimes it doesn't. So it kind of gets the right idea, but it's sometimes a little bit off because this combination has never been trained. So what you can then do is you can take this as initialization and then fine-tune it from there. Okay, does anyone have any questions about the architectures for multitask transfer? Yes?
Is there any advantage doing like a distillation here? Because I don't think it's much harder to run a test time for this.
Yeah, so the question is there any advantage to doing distillation here? I think you probably could, but you just have to be very careful because the whole point of doing this is that some of these things are they're not compatible just in terms of the data types. So you can't, for example, have a policy trained for a 3-link robot, output actions for a 4-link robot, at least not without some very clever architecture tricks. Yes, question back there.
Going back to the example of different camera inputs, where you have sort of camera input and the lidar input,
Mhm.
and you have like say different driving possibilities,
Mhm.
different cities, right? So what we're doing in this case is we're explicitly designing the structure so that for different camera inputs, like same camera input, different cities have like a common input,
Yeah.
or like lidar but different cities.
Right.
have a common
Well,
input.
so what you're really designing is you're just designing you're designing in the fact that the tasks that have shared components, or the tasks that have shared properties will share neural network components. You're not actually doing anything special to choose the form of that component, although probably if you have images you want to use a convnet and so on. But really the point is just choosing the right network from your set of networks, not necessarily doing anything very clever with its internal plumbing.
Right, but my question was sort of, in this case, we're still choosing which tasks have shared components.
That's right, yeah. So you need to know which tasks have shared components in order for this to work. Now in some cases it's impossible to miss. Like if you have a camera versus LiDAR, you need to, they have different inputs, so you need to somehow input that into the network. You could imagine doing some sort of like expectation maximization style procedure to actually infer which parts need to go together. And people have studied that not necessarily in the context of reinforcement learning, but in the context of modular networks for supervised learning problems. that's something that people have looked into, how to basically infer the structure. And probably things like that can be extended to RL as well. Okay. So, summary for multitask learning. Multitask learning is good because the more tasks you have, the more variety there is, the more likely you are to generalize. And it's often easier to obtain multiple different but relevant prior tasks than it is to obtain one kind of perfect source task. So that makes this a good combination. You can do model-based RL for multitask transfer in the hopes that the laws of physics essentially transfer better than a particular task-specific policy. You can do distillation to combine multiple policies into one policy. If it's ambiguous from the input what it is that you're supposed to be doing, like with the dishes in the laundry, then you can use a contextual policy where you give it additional input to tell it which task it's supposed to be doing at any given time. And you can choose special architectures, especially for the case where you have different size inputs and different size outputs that make use of modularity. Okay, some suggested readings about multitask learning. This is the model-based paper that I discussed. This is the paper on policy distillation, and this is the paper on actor mimic. So these two both look at distilling from multiple Atari games into a single policy. This is the modular networks paper. Yeah, that's it. So the third part for transfer learning is meta-learning, and this will be covered on Friday in a guest lecture by Chelsea Finn, so I'd encourage all of you to go to that, especially if you're interested in doing the meta-learning portion for homework 5, because that's where we'll introduce all the concepts you need for that. So see you next time.